Grasp detection is one of the fundamental problems in robotic manipulation. Existing methods have achieved promising results on various open datasets. It is noteworthy that these datasets predominantly adhere to a homogeneous assumption of the physical properties and focus on textures and geometries. Thus, existing grasp algorithms rely solely on geometries and textures will fail to effectively lift an object due to the oversight of variations in part density or friction coefficients. An example is shown below, where two hammers with the same shape but different mass distribution. Existing methods cannot differentiate the differences solely from the visual depth input and would fail to precisely grasp the heavier part of the object, as we tested in both simulation and real-world scenario. We explicitly construct various objects with distinct mass distributions and friction coefficients, frame this challenge as a few-shot learning problem, wherein the physical properties of each object must be gleaned from contextual information derived from a limited number of grasp trials, and present a meta-learning grasp framework called Condex to acquire knowledge of these properties purely from depth images. Lastly, we demonstrate substantial advantages in real-world object manipulation, despite being trained exclusively in a simulated environment. We generate objects and changing physical properties by disassembling them into small components. Various physical properties can be obtained by varying the mass density, friction coefficient, and size of each component. Afterwards, we use two simulators, namely PyBullet and Majoko, to collect the grasp datasets by running the grasp manipulation on each object instance with 30 rollouts. In total, our dataset contains 63,000 depth images with grasp labels for letters dataset and 20,160 for bottles dataset. Since we frame the task as a few-shot learning problem, the collected data will be split randomly into context and target sets for each object. The context set includes the depth images, the distance between the grasp candidates and the gripper, and the binary grasp labels indicating if the grasp succeeds, while the target set lacks labels during the inference phase. Condex learns the physical properties of each object from context set and predict the confidence score of each grasp respectively. Condex contains an encoder, a permutation invariant aggregator, and a decoder. The physical properties are encoded as a task representation R. Condex outperforms baselines on both letters and bottles datasets and yields valuable information from diverse context pairs and adapts effectively to previously unseen tasks. Experiments on a real Franca robot involves a successful grasp results in the bottle being successfully placed inside the designated box. The bottle is filled with different quantities of material to acquire diverse mass distributions. Condex outperforms DexNet significantly. Furthermore, the performance with more contexts is improved, indicating Condex is able to extract useful information from real scenes, although trained fully with synthetic data.